Hi everyone, my name is Linguan from the University of Waterloo. Today I'm going to talk about Natto, a distributed database system that provides transaction prioritization. And this project was done in collaboration with my colleagues Xinan and Bernard at the University of Waterloo. And this work was motivated by many number of applications that requires different priority levels for the transactions. One example is that many companies provide infrastructures for different applications that have different requirements. Some applications are user-facing, which requires low latency. It should differentiate service time for the different applications. Another example is the trading platforms. These platforms may offer their institutional customers a higher priority processing for their time-sensitive trades. To provide transaction prioritization in a single server database system, we can create separate queues for different priority levels and process transactions starting from the highest priority queue. But many applications have data stored in different data centers across the world. To manage this data, the applications may use distributed database systems such as Google Spanner, Cockroach DB, or Carousel. Carousel is our previous work that provides low latency transaction processing. It is much difficult to provide a prioritization because the data is partitioned and stored in the different locations. A transaction may touch one or more partitions. Only the participant partition can see this transaction. There's no centralized view of the transactions. Without a global view, servers will perform operations independently that may conflict with other servers. As a result, it leads to higher abort rate or even deadlocks. In order to establish a global ordering of the transactions, one possible solution is to use a centralized scheduler. For example, Kelvin uses a logically centralized sequencer to order its transactions. It is a relatively easy solution and provide all the information. But in the geo-distributed environment, it introduces additional round trips. The centralized scheduler is in a single location. It may be far from the servers. As a result, it will significantly increase the latency. Also, the scheduler itself may become a performance bottleneck, and often it restricts to non-interactive transactions. Another way is to use a distributed scheduler, but it is more challenging to build. First, we want to avoid a coordination overhead. If we introduce a lot of coordination, it is no better of the centralized scheduler. Second, there is no global view. As we mentioned previously, without global view, it also can have a bad performance due to the high abort rate. That makes us to build Natto. It uses timestamp to establish a global ordering of the transactions across the different partitions. Unlike the classic timestamp approaches, which assigns the timestamp when the transaction commits, instead, we are using timestamp based on the arrival time of the transactions, not the arrival time at the closer partition, but the furthest partition. Because the furthest server determines the overall transaction processing time, the timestamp can not only give us a way of ordering the transactions, but also give us opportunities to provide transaction prioritization. It allows us to perform priority abort and the conditional prepare. To further reduce the latency, we introduce another optimization called the early committed state forwarding. Our solution targets 2FI transaction instead of the general transactions. 2FI transaction is proposed in our previous work, Carousel. 2FI transaction has two rounds. There is a read round followed by a write round. Fixed that means all the keys are known ahead of time. It is an interactive transaction allowing user abort, very general, and can be used in many situations. By restricting the transaction model, it gives us more flexibility to perform scheduling because we know all the partitions that transactions are going to touch and when the transaction will be end. Now we have 2FI transactions. Let's see how to process 2FI transaction in the platform such as Carousel. In this example, we have the client that is co-located with a transaction coordinator and the two partitions. The latencies between the client and the partition 1 and 2 are 10 milliseconds and 25 milliseconds. In 2FI transactions, we know all the keys ahead of time, so we can send both read and prepare requests in one message to all participant partitions. Leader 1 receives the request and sends the read result back to the client. In the same time, it also sends the 2PC prepare message to the coordinator. Later, partition 2 receives the request and does the same process. It replies the read results to the client and sends the 2PC prepare message to the coordinator. Once the client receives all the read results, it can commit the transaction by sending the commit request to the coordinator. After receiving the client commit request and the 2PC prepared message from both partitions, the coordinator sends the commit result to both client and the participant partitions. In this example, we can see that even though the partition 1 processes a transaction at T0 plus 10 milliseconds, we still need to wait partition 2 to process this transaction. Therefore, we observe that the furthest partition decides the overall transaction processing time. As a result, even if the partition 1 received the transaction at T0 plus 10 milliseconds, we can delay the execution until T0 plus 25 milliseconds, and it will not affect the overall transaction processing time. In fact, it provides us a window of time to schedule the transactions. In this example, there's the 15 milliseconds window on partition 1. If this is a low priority transaction and a high priority transaction arrives during this window, now we have the opportunity to abort the low priority transactions. Otherwise, we won't have this opportunity if we process the transaction right away after we receive it. We assign the arrival time at the furthest partition as a transaction timestamp. In this case, it is T0 plus 25 milliseconds. In order to estimate the arrival times at the servers, client sends a probing message to the server, and the server returns its local time back to the client. It is a very simple approach, but it works well. In our previous work, Domino, we did an experiment on Azure showing that the network delays are relatively stable so that we can have accurate estimate. In the experiment, we found that the accurate prediction rate is about 94%. Now we have the transaction timestamp. Let's see how to use this timestamp to provide the prioritization. First, the technique we are introducing is priority abort. In this example, we have 2 clients and the partition leaders. The latency between the client 1 and the leader 1 is 10 milliseconds. The client 2 is 20 milliseconds away from the leader 1. At time 0, both clients send the transactions. Transaction 1 is the low priority transaction, and the timestamp is T0 plus 25 milliseconds. Transaction 2 is a high priority transaction, and the timestamp is T0 plus 30 milliseconds. They have conflict on the partition, otherwise we will process the transaction in parallel. The leader 1 received the transaction 1 first. Instead of processing it right away based on the transaction timestamp, leader 1 buffers the transaction until its execution time. Then leader 1 received the transaction 2, which is the high priority transaction. Since we don't want the high priority transaction to wait for the low priority transaction, and we haven't processed the transaction 1 yet, we want to abort it, and the high priority transaction will not be blocked. Delaying the execution of the transaction 1 gives us the scheduling opportunities, and the timestamp tells us how long the transaction should wait without penalty. This approach works well in many cases, but what if the high priority transaction arrives after the low priority transaction is prepared? In this case, the priority abort does not work. Therefore, we introduce our second technique, conditional prepare, to solve this case. Let's continue the example and see how conditional prepare works. Here is another partition, and both transactions also have conflict on this partition. It received the transaction 1 at T0 plus 25 milliseconds. Thinks now it's time to execute the transaction 1, and there's no concurrent conflict transaction, leader 2 prepares transaction 1. Then it received the transaction 2, which is a high priority transaction, but the transaction 1 already prepared on this partition. Transaction 2 has to wait for the low priority transaction. It may take some time because transaction 1 may need a couple of round trips to However, the server has more information. Specifically, it knows the keys that transaction 1 and transaction 2 touch, and the arrival times at all the partitions. In this example, it knows transaction 1 arrives at leader 1 at T0, and transaction 2 arrived at T0 plus 20 milliseconds. By using all this information, leader 2 can guess that it is very likely the leader 1 has already aborted the transaction 1. As a result, even if transaction 1 is not completed yet, leader 2 will prepare transaction 2 anyway, but conditionally. The condition is that the transaction 1 is actually aborted by the coordinator. Once the condition is satisfied, we can then complete the transaction 2. By doing so, it reduces the processing time of the transaction 2. It requires some communications between the coordinators of the both transactions. Natto also has another optimization called early committed state forwarding. It allows uncommitted data to be forwarded because the system is designed based on the carousel. Even if it is uncommitted, we know it is fault tolerant. This allows us to safely reduce the latency for both low and high powered transactions. Because of time, I can't talk about this into detail. The information can be found in the paper. We evaluate Natto by comparing with both carousel basic and fast, taper, and the spanner-like systems that use preemption and preempt on wait for the transaction prioritization. We run the experiment on Microsoft Azure, AWS, and our local cluster. We deploy the system across 5 data centers with 3 replication factors and 5 data partitions. We use 3 workloads for this evaluation: YCSVT, retweets, and the small bank workload. And we set 10% of the transactions as high priority. The first graph shows the 95th percentile latency of the high-powered transactions as increasing the transaction input rate. When the input rate is low, carousel, taper, and the Natto have similar performance due to the low contention. The spanner-like system has higher latency because they require additional round trips. As the input rate increases, the latency of other systems increases rapidly. To fit everything in the same graph, there is a huge break in the middle. Above this break, the latency is over 2 seconds. The latency difference between the Natto and other systems are significant. This is because as the contention increases, the abort rate increases. It requires multiple round trips to commit the transaction. With only timestamp, Natto's latency also increases to the level that's similar to the performance of the spanner-like system without contention. Once we introduce all the optimizations, the increase in latency for high-power transaction is minimal. Next, let's see what happened when we change the popularity distribution of the keys. It turns out the effects are similar. Initially, when the ZIF coefficient is low, it looks similar as when the input rate is 100 transactions per second in the previous graph. Again, there's a huge break in this graph. As we increase the ZIF coefficient to 0.95, the latency difference is also huge. Natto's latency also increases. This is mainly due to the contention between the high-powered transactions, not between low and high-powered transactions. What I have shown so far is the performance when the network estimates are accurate. In some cases, the network may not be stable, so that the estimate is not accurate. This graph shows the performance when we increase the network delay variance. We found that it does affect our overall latency due to the overestimate or underestimate the latency. However, in a managed data center, we may not see 40% network delay variance. It is much likely at 10% instead of 40%. In conclusion, many applications have different latency requirements for different transaction types. To meet such requirements, it is critical to support prioritization. Natto does this in a distributed way. By using network measurements to estimate the transaction arrival time at the furthest partition, it establishes a global ordering of the transactions and gives us opportunities to provide the transaction prioritization. With all the optimizations, Natto can significantly reduce the tail latency of the high-power transactions, and it is robust against to the network variance. Thank you.